Okay, let's unpack this. Today we're taking a deep dive into SQL, the foundational language of data. We're looking at a collection of common SQL concepts and challenges, but don't let the common part fool you.
Right.
This isn't just about memorizing answers. It's really about extracting the essential knowledge and maybe some surprising insights that make you truly well-informed about how data is structured, queried, and optimized.
Precisely. These seemingly straightforward questions, they act as excellent prompts to explore core concepts that are critical for anyone working with data, really.
Yeah.
Our mission today is to distill the most important nuggets from these areas, helping you understand not just what the answer is, but why it fundamentally matters in the bigger picture of database management.
We've got some fascinating ground to cover here, from understanding what SQL actually is to tuning your queries for like lightning-fast performance.
Yeah, the performance bit is key.
And even designing databases that are, well, virtually bulletproof. So let's get started.
Sounds good.
Okay, a common point of confusion right out of the gate.
Yeah.
We hear SQL and MySQL tossed around almost interchangeably sometimes. Are they the same thing, or is there a crucial distinction we need to grasp?
Yes. It's a classic mix-up, definitely. Think of SQL, structured query language, as the universal language for talking to databases.
Okay, the language itself.
Exactly. It's the set of commands used to query, insert, update, delete data, and also to define the structure, the schema of your database. MySQL, on the other hand, is a specific relational database management system,
Right.
an RDBMS.
Gotcha, so like the software.
Precisely. It's the software that actually implements that SQL language. It provides the platform to store, manage, and retrieve your data. So, yeah, SQL is the language, and MySQL is just one of many popular engines that understands and uses that language.
Like English and a specific novel.
That's a great analogy. English is the language. A novel is written in English. Other RDBMS systems you've probably heard of, like Oracle, Microsoft SQL Server, PostgreSQL, they all speak SQL too.
Right, right. So SQL isn't just one monolithic thing. It has different aspects, different categories of commands within that language.
Exactly. SQL is typically broken down into different sort of sub-languages or command categories, each serving a distinct purpose.
Okay.
First, there's DDL, that's data definition language. These are the commands for defining or modifying the structure of your database. Your create table, alter table, drop table. It's all about the blueprint.
Building the house, basically.
Yeah, good way to put it. Then we have DML, data manipulation language.
Right.
This is for manipulating the data inside those structures. This is your day-to-day stuff. Select to get data, insert to add it, update to change it, delete to remove it.
Got it. DDL for structure, DML for data.
Correct. Next up is DCL, data control language. This is all about managing rights and permissions. Who can do what? Think grant access, revoke access, security stuff. Very. And finally, TCL, transaction control language. These commands handle database transactions, making sure operations happen reliably, especially when there are multiple steps. Things like commit to save changes permanently or roll back to undo them if something goes wrong.
Okay, that makes sense. DDL, DML, DCL, TCL, different jobs for different commands.
Yeah.
And before we dive deeper into queries, a quick but I think incredibly practical distinction, one that can trip people up and silently affect performance.
Yeah.
Sure versus varchar 2. Seems small, but these details matter, don't they?
They absolutely do. This is a great example of a seemingly minor choice with real practical implications for storage and efficiency. Sure is used for storing fixed-length strings.
It's like.
So if you define a column as sure, it will always allocate and store 10 characters. Always. Even if your input is shorter, like hi, it pads the rest with spaces.
So hi and assure uses all 10 bytes.
Exactly. It pads the remaining 8 with spaces. You can't store anything other than 10 characters, effectively.
Okay, and varchar.
Varchar 2, however, is for variable length strings. If you define varchar tune, it means it can store any length of string up to 10 characters. But crucially, it only uses the space needed for the actual data, plus a tiny bit of overhead to store the length. So hi in varchar 2 might only use, say, 2 or 3 bytes of actual storage. This makes varchar 2 way more flexible and usually much more efficient for varied text data. It doesn't waste space on padding.
Which I imagine adds up quickly in large databases.
Massively. Think about addresses, names, descriptions, rarely fixed length.
Yeah.
Using Chartfor for those can lead to huge storage bloat and slower I/O because you're reading and writing all those extra spaces.
Right. That's a perfect example of a small detail scaling into a big problem.
Yeah.
Okay, let's get into the nitty-gritty then. Making our SQL queries really perform well. We have a whole section here on How to tune your SQL query for better performance. What are the core principles, the guiding lights here?
Well, what's fascinating is how seemingly small choices in your query structure can just dramatically impact performance, often exponentially,
Oh,
actually.
yeah.
The core principle is pretty simple, though. Minimize the amount of work the database has to do. Avoid common pitfalls that force it to scan more data, do more operations, use more resources than absolutely necessary.
Makes sense. Give me your rule number one.
Okay, key rule. Specificity over wildcards. Always select the specific fields you actually need instead of the very common select at.
Select. The
Yeah.
lazy option.
It feels easy, but it's often terrible for performance. Why? Because select fetches all columns, every single one. That can include tons of unnecessary data, especially with wide tables.
Right.
That means more data read from disk, more data sent over the network, more data for the database engine to handle. At scale, this can seriously choke your system. It hogs network bandwidth, eats up memory.
Turning a potentially fast query into a crawl.
Exactly. It's not just inefficient, it can be actively harmful in large systems.
Can you give a sort of classic real-world example where select caused real pain?
Oh, easily. Think analytical dashboards or reports. Maybe a dashboard only needs, say, 5 columns from a user table that has 50 columns. If the query uses SelectBert, every time someone refreshes that dashboard, it pulls 45 columns of completely useless data across the network and into memory.
Yikes.
Multiply that by hundreds or thousands of users hitting refresh, and yeah, your database server gets overwhelmed just transferring junk data, latency spikes, maybe even crashes, all because of that little asterisk.
Okay, lesson learned. Be specific. What's next?
Next, think twice about select distinct. Avoid it when you can. It seems handy for getting unique values, sure, but it forces the database to do a lot of extra work.
How so?
It has to group and sort all the data by every column you selected just to find and eliminate the duplicates.
Yeah.
That's a really time-consuming operation, especially on large data sets. It hammers the CPU and often spills over into using temporary disk space, which is super slow compared to memory.
So use it sparingly, only when absolutely necessary.
Precisely. Another critical point, how you join tables. Always create joins using an explicit inner join syntax, rather than listing tables in the from clause and putting the join condition in the where clause.
The old style, like from table A, table B, where table A dot A, can table B.
That implicit join syntax. The danger is, if you forget the where condition or get it wrong, you can accidentally create a Cartesian product.
Which is bad.
Very bad. It means every row from the first table gets combined with every row from the second table. If you have 1,000 rows in each, suddenly you're dealing with 1,000,000 rows.
Oh.
Inner join, on the other hand, specifically gets only the records that match based on your on condition. It's much clearer and much safer, filtering out non-matching rows immediately. Far more efficient.
Okay, be explicit with joins. That makes sense. That naturally leads us to filtering itself where versus having. This is a classic one. I've seen even experienced folks get tripped up by the performance difference here.
Absolutely. Understanding where versus having is a key indicator of optimization altering. It really boils down to when the filtering happens in the query executing process.
Right.
Having filters after grouping. So the database fetches the whole table, or at least the relevant parts, applies the group by aggregation, calculates counts or sums or whatever, and then having filters those aggregated results.
For example.
Like select department, AVG salary, from employees group by department having AVG salary 50,000. It calculates the average salary for all departments first, then throws out the ones below 50K.
Okay, yeah.
Where it filters before grouping, it filters the individual rows before they even get considered for aggregation. So if you only wanted the average salary for the sales department, you'd write select department, AVG salary, from employees where department, sales group by department. The where clause throws out all non-sales employees first. The group by and AVG only have to work on a much smaller set of data.
Much more efficient. Filter early, filter often.
That's the mantra. Don't aggregate data you're just going to throw away later. If you can filter it out first with where, it can be orders of magnitude faster. It's like, don't bring rocks to the picnic if you only want sand.
I like that. Filter early, filter often. Any other quick hits for performance tuning?
Yes. Definitely minimize joins. Each join adds complexity and processing overhead. Only join tables when you absolutely need data from them. Too many joins, especially on large tables, can really slow things down.
Makes sense.
And finally, a big one. Avoid cursors at all costs if you can. Cursors process data row by agonizing row.
RBR, row by agonizing row.
Exactly. It breaks the whole set-based nature of SQL. Cursors consume lots of memory, create locks, cause high I/O. They just kill performance compared to set-based queries that operate on the entire result set at once. Use them only as a last resort when set-based logic is impossible.
Okay, solid advice. Avoid select and row. Be careful with distinct. Use inner join explicitly. Filter with where before having. Minimize joins, and steer clear of cursors. Got it.
That covers a lot of the big performance wins.
So we know joins are crucial, and we need to use them carefully. But what are the different types beyond inner join? When do we use each one? This seems fundamental to knitting together data correctly.
Absolutely. Joining is how we bring related pieces of information together from different tables. Understanding the types is key because each one handles matches, and importantly, non-matches differently.
Right, so we know inner join, that's the workhorse, right?
Yep.
Finds only the matching rows.
Correct. It's the intersection.
Yeah.
Only rows where the join condition is met in both tables make it into the result. If an employee doesn't have a matching department ID in the departments table, they won't show up in an inner join between employees and departments.
Okay. What about when you want to see those employees, even if their department is missing or null?
That's where the outer joins come in. They intentionally keep rows from one or both tables, even if there's no match.
Okay.
The left outer join, often just called left join, retrieves all rows from the table on the left side of the join keyword, and it retrieves any matching rows from the right side table.
And if there's no match on the right?
Then you get NLL values for all the columns from that right side table for that row. It's perfect when you want to see everything from one primary table plus any related info that exists in another, like show me all customers, and if they have placed an order, show the order details.
Got it. So right outer join is just the opposite.
Exactly. Right join keeps all rows from the right-hand table and matching rows from the left. If there's no match on the left, you get NL for the left table's columns. Same principle, just mirrors the logic.
And full outer join.
That combines both. It returns all records from both tables. If a row from the left table has no match on the right, it shows up with NLLs for the right table columns. If a row from the right table has no match on the left, it shows up with NLLs for the left table columns. And matching rows show up with data from both.
So it gives you the complete picture matches, left-only and right-only records.
Precisely. Useful for things like reconciliation tasks where you need to see everything from both sides.
Okay, inner, left, right, full outer. What else? You mentioned specialized ones.
Yep. There's the self join. This is where a table joins with, well, itself.
How does that work? Why would you do that?
You use table aliases to treat the same table as two separate instances. It's useful for comparing rows within the same table. For example, finding employees who report to the same manager, you join the employee table to itself on the manager ID column. Or maybe comparing product prices from different time periods within the same product table.
Ah, okay. Comparing rows to other rows in the same table. Clever.
Then there's the cross join. This one produces the Cartesian product we talked about avoiding earlier.
Right, every row combined with every other row.
Exactly. Rows in table 1, rows in table 2. It's rarely what you want for meaningful data relationships because it generates this huge, usually meaningless result set. But it can occasionally be useful for generating all possible combinations, maybe for test data generation or specific combinatorial problems.
Use with extreme caution, then.
Definitely. And lastly, the natural join. This one's a bit different. It implicitly joins tables based on all columns that have the same name and data type in both tables.
So you don't need an own clause.
Correct. It figures it out automatically based on matching column names. For example, if table A has ID, name, and table B has ID, salary, a natural join between them would automatically join on the ID column.
Sounds convenient.
It can be, for simple cases, but it's often considered a bit risky in production environments.
Why's that?
Because if someone later adds a new column with the same name to both tables, maybe for a completely different purpose, the natural join logic will suddenly, unintentionally change. It will start joining on that new column too, potentially breaking your query in subtle ways. It's usually safer to be explicit with an on clause using inner join or outer join.
Good point. Explicit is often better than implicit magic. Okay, that covers joins pretty well. Let's shift to the big picture now. Designing databases, how do we structure them so they're reliable, flexible, and avoid those nasty problems like data corruption or loss? Let's talk normalization and the famous ACID properties.
Right. If we connect this to the bigger picture, these concepts, normalization and ACID, they are truly foundational for building robust, scalable systems. Systems that maintain data integrity over the long haul. It's not just about storing data. It's about ensuring its quality and reliability.
Okay, let's start with normalization. What is it and why bother?
Normalization is basically a systematic process. It's about organizing the data in your database, specifically structuring your tables and columns, to reduce data redundancy and improve data integrity.
Reduce redundancy, meaning don't store the same piece of information in multiple places.
Exactly. The core idea is, if you find yourself repeating the same group of data across multiple rows in a table, you should probably break that repeating data out into a new separate table and link the two tables using keys.
Okay.
This prevents you from having to store, say, a customer's full address with every single order they place. You store the address once in a customer table and just link the order to the customer ID. We usually aim for different stages or normal forms, a 1NF, 2NF, 3NF are the most common.
And the opposite is denormalization.
Right. Denormalization is the opposite process. It's intentionally introducing redundancy, often by bundling data back together into fewer tables, maybe even duplicating data.
Why would you ever want to do that? This is like a step backwards.
Well, sometimes, very carefully, it can be done to improve read performance for specific, very frequent queries. By having all the data in one place, you might avoid some expensive joins, but it's a trade-off.
What's the downside? What are the actual problems, the headaches, if we don't normalize or if we denormalize too much?
Denormalized data sets suffer from what we call anomalies. These are problems that pop up when you try to insert, delete, or update data, and they can lead to inconsistencies or even data loss. There are three main types. First, insertion anomalies. You might not be able to insert a piece of data unless you have all the other related data that's crammed into the same denormalized row. For example, imagine one big table for orders, products, and customers. If a new product arrives but hasn't been ordered yet, how do you insert it? You only have product info. You'd have to put NLLs for all the customer and order columns, leading to incomplete records, or maybe you couldn't even add the product until it's ordered.
Right, you can't record part of the story.
Exactly. Second, deletion anomalies. Deleting one piece of information might accidentally wipe out other unrelated but valuable information stored in the same row. In that same example table, if a customer cancels their only order for a specific product, deleting that order row might also delete the only record of that product's details if it wasn't ordered by anyone else. You lose the product info just because an order was deleted.
Ouch, that's bad.
Very bad. And third, updation anomalies. If a piece of data that's repeated needs to be updated, you have to find and change every single instance of it. If a product price changes, and that product is listed in hundreds of order rows in your denormalized table, you have to update the price in all 100 rows. If you miss one, you have inconsistent data.
Nightmare.
Whereas in a normalized design, the product price lives in one place, the products table. You update it once, and it's instantly consistent everywhere because other tables just link to it.
So normalization prevents these anomalies by ensuring data lives in only one logical place. And those normal forms, 1NF, 2NF, 3NF, briefly, what do they target?
Briefly, yes. 1NF, first normal form, is the most basic. It just means each column cell holds a single atomic value, no lists or repeating groups within a cell, and each row is unique, usually via a primary key. 2NF, second normal form, requires 1NF and it tackles partial dependencies. This means that all non-key columns must depend on the entire primary key, not just part of it. This applies when you have a composite primary key made of multiple columns. 3NF, third normal form, requires 2NF and it eliminates transitive dependencies. That's where a non-key column depends on another non-key column, which in turn depends on the primary key. So A depends on B and B depends on C. Key. 3NF says A should depend directly on C.
Okay, so progressively stricter rules to eliminate redundancy and dependencies. 3NS is often considered the sweet spot.
Generally, yes. For most transactional databases, OLTP systems, 3NF strikes a good balance between data integrity and performance. Higher forms exist, but often have diminishing returns or can even impact performance negatively sometimes.
Okay, so we've structured our data well using normalization.
No.
Now, how do we ensure the operations on that data? The transactions are reliable, consistent, and safe, especially with many users hitting the database at once. That brings us to ACID, right?
Exactly. The ACID properties are the bedrock guarantees for database transactions. They ensure data is handled reliably, which is absolutely critical in systems dealing with, say, financial data, inventory, bookings, anything where data integrity is non-negotiable, even if the system crashes or multiple things happen concurrently.
Okay, let's break down ACID. A is for
Atomicity. A transaction is treated as a single, indivisible unit of work. It's all or nothing. Either all the operations within the transaction complete successfully, or none of them take effect. If any part fails, maybe a network error, a power outage, the entire transaction is rolled back, leaving the database exactly as it was before the transaction started.
like a bank transfer. Debit A, credit B. If the credit fails, the debit must be undone.
Perfect example. That's atomicity. Next is C for consistency. A transaction must bring the database from one valid state to another valid state. It must preserve all the defined rules and constraints, things like unique keys, foreign key relationships, data types, maybe business rules like account balance cannot go below 0. If a transaction would violate a rule, it's rolled back.
So the data is always structurally sound and follows the rules.
Correct. I stands for isolation. This means that concurrent transactions should occur independently of one another without interfering. Changes made by one transaction shouldn't be visible to other transactions until the first one is committed. This prevents problems like dirty reads, reading uncommitted data, or lost updates. It makes it seem as though transactions are running one after another, even if they're running in parallel.
So my transaction doesn't get messed up by yours happening at the same time.
Essentially, yes. The database manages locking or other mechanisms to ensure this isolation. And finally, D is for durability. Once a transaction has been successfully committed, its changes are permanent and will survive any subsequent system failures, like a crash or power loss.
So committed data is safe.
Yes. The system ensures committed data is written to persistent storage, like a hard drive or SSD, so it's still there after a restart or recovery. That bank transfer, once committed, stays committed.
Atomicity, consistency, isolation, durability, acity, the pillars of reliable transactions.
They really are.
And underpinning a lot of this, the normalization, the consistency, the performance, we have different types of keys and indexes, right? These are the actual mechanisms that enforce structure and speed things up.
Absolutely. Keys are about defining identity and relationships, while indexes are primarily about performance, making data retrieval faster.
Okay, let's talk keys first. We mentioned primary keys already.
Right. The primary key uniquely identifies each row in a table. Crucially, it cannot contain any ELL values. Every table should ideally have one.
What about a unique key? Sounds similar.
It is similar in that it also enforces uniqueness for all values in a column or set of columns. The key difference is a unique key can allow one NUL value in most systems, whereas a primary key cannot allow any NULs. A table can also have multiple unique keys while it can only have one primary key.
Okay. And candidate key.
A candidate key is any column or set of columns that could potentially serve as the primary key, meaning it's unique and non-null. You might have several candidate keys in a table.
Yeah.
You then choose one of those candidate keys to be the official primary key.
Got it. And the really important one for relationships, foreign key.
Yes, the foreign key is the glue that links two tables together. It's a column, or columns in one table, that references the primary key of another table. This enforces referential integrity. Meaning you can't, for instance, insert an order for a customer ID that doesn't actually exist in the customer table. The foreign key constraint prevents that, ensuring your references are always valid. It also typically prevents you from deleting a parent row, like a customer, if there are still child rows, like orders, referencing it, unless you explicitly set up cascading rules. It stops you from creating orphan records.
Super important for keeping related data consistent.
Absolutely fundamental.
Okay, now indexes. They're all about speed.
Primarily, yes. Indexes are special lookup tables or structures that the database engine can use to speed up data retrieval operations on a table, dramatically reducing the need to scan the entire table.
Like an index in the back of a book.
Exactly like that. There are two main types, clustered and non-clustered.
What's the difference?
The clustered index actually determines the physical order in which the data rows are stored on disk. It sorts the table based on the clustered index key. Because the data can only be physically stored in one order, a table can have only one clustered index.
Only one. And the data itself is stored in that index structure.
Yes. The leaf nodes of the clustered index are the actual data rows. Many systems default to creating a clustered index on the primary key because lookups by primary key are so common. Clustered indexes are generally very fast for range queries, like finding all orders between two dates, because the relevant data is physically next to each other on disk.
Okay. And non-clustered.
A non-clustered index is more like that book index analogy. It's a separate structure that contains the index key values and a pointer, like a row ID or the clustered key value, back to the actual data row in the main table heap or clustered index.
So it doesn't change the physical order of the data.
Correct. The data stays where it is. The non-clustered index just provides a fast way to find the location of specific rows. Because it's a separate structure, you can have multiple non-clustered indexes on a single table, often hundreds.
Why have multiple?
To speed up different kinds of queries, you might have one on the customer's last name, another on their city, another on their sign-up date. depending on what columns are frequently used in where clauses or joins.
Are they slower than clustered indexes?
For range queries, often yes, because finding the pointers in the index and then doing separate lookups for each actual data row can be slower than scanning the physically contiguous data in a clustered index. But for specific point lookups, find customer with ID 123, they are very fast. The trade-off is that every index you add slightly slows down insert, update, and delete operations because the indexes also need to be maintained.
Right. More indexes mean faster reads for some queries, but potentially slower writes. A balancing act.
It's always a balancing act in database design and tuning.
Wow. We've really covered a significant landscape today. From, the core identity of SQL and its different command types through the crucial art of optimizing queries for speed, understanding all those different ways to join data, and finally diving deep into the really robust principles of database design, normalization, ACID keys, indexes.
Yeah, and what's fascinating here is that these aren't just, theoretical concepts or abstract interview questions. They are the practical day-to-day backbone for creating efficient, reliable, and well-structured data systems. Whether you're building a massive e-commerce site or just trying to pull the right insights from your own data.
Right.
Mastering these distinctions, these best practices, it really empowers you to interact with data far more effectively, to turn potential performance pitfalls into, well, advantages.
So what does this all mean for you, the listener? I guess the next time you're working with data, maybe querying a database or even thinking about designing one, ask yourself some of these questions. How normalized is this data? Am I risking subtle anomalies down the line? Is my system built on a solid AC foundation, ensuring those transactions are truly reliable? Am I joining tables efficiently? Am I selecting only what I need, or am I creating a hidden performance bottleneck for myself or for others later?
And if we connect this back to the bigger picture, just considering the depth and the implications of what are often considered just common SQL concepts, it really highlights how much more there is to explore in the world of data. How foundational this seemingly simple language is to almost every digital interaction we have today.
Absolutely. What other hidden complexities and powerful tools might be lying just beneath the surface of the data you interact with every day, just waiting for you to deep dive into them? Something to mull over until our next deep dive.